Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Chemical Reaction Engineering Part 2, Analyzing Chemical Reactor Performance. Understanding reactor performance terminologies. Understanding the reactor performance terminologies is a first step in analyzing reactor performance. Chemical reactors are designed to achieve well-defined performance objectives. The main objective of a process plant is to achieve the design production capacity of the plant. Take a look at this picture. It is an illustration of a chemical processing plant. It consists of reactor, separation units consisting of series of separation equipment, and product storage tanks. Reactor is the heart of the plant. It is a reactor performance that makes the process economical or not. Raw material consumed per ton of product is a key determining factor that decides whether the process will be profitable. If it is a catalytic process, catalyst volume is also important. Hence, from production cost point of view, you must understand the key reactor performance parameters. Having understood the relevance of reactor performance parameter, let us get into the main part of the discussion now. Shown in this figure is a plug flow reactor. Reactant A reacts to form product B and C in the first reaction. The product B that forms the first reaction further reacts to form D. So the reactor outlet contains unreacted A, products B, C and D. In any reaction process, it is often possible that unwanted additional reactions occur. It may be that the desired product is consumed and converted to unwanted product by some series or consecutive reactions. In some other cases, it may be that there are parallel reactions occurring between the reactants, thus diverting the reactants for undesired product. What is happening is that there is a competition between the reaction. The focus of chemical reaction engineering is to optimize the operating conditions or reactor design so that we get closer to the desired reaction pathways. Since there are multiple reaction pathways, we have to measure the reactor performance by suitable terminology. The reactor performance is measured in terms of conversion, selectivity, and yield. Now let us move on to understand what these terms actually means when it is applied to analyzing reactor performance. First, conversion. Conversion is defined as the amount of reactant converted per pass. In other words, it is the amount of reactant disappeared. It is a ratio of reactant A in the inlet in weight percent minus reactant A in the outlet in weight percent to the reactant A in the inlet in weight percent. The second term applied to analyze reactor performance is selectivity. Selectivity is the ratio of the main product B produced to the total product produced by all reactions, both parallel and series reactions. This means how much of the product stream is a desired product B. Expressing is in an equation, selectivity is the ratio of mass of product B in the outlet to the mass of total product in the outlet. This definition for selectivity is product based. Another definition for selectivity is a ratio of mass of A consumed for the main product B to the total amount of A consumed for all reactions. This definition is based on the raw material consumption. This means how much of reactant A is selectively consumed for the desired product B. Selectivity based on products is generally used for analyzing reactor performance. So do not confuse with the definition. It is only to understand the terminology in different contexts, which will help us to understand the process better. Selectivity provides information about the complexity in the downstream separation units. Lower selectivity means more byproducts due to side reactions, hence difficult separation processes. The third important performance metric in analyzing reactor performance is yield. Yield is a ratio of the amount of product B produced to the maximum possible amount of product B would be produced if there were no side reactions. So yield is given by mass of product B in the outlet divided by maximum possible amount of B would be produced if there were no side reactions. Significance of conversion and selectivity. Conversion and selectivity has a significant impact on the production cost. Higher conversion means lower recycle flow rate and processing cost. Higher selectivity means greater amount of desired products and less byproducts. Undesired side reactions can produce byproducts whose boiling points may be lower or higher than the desired product. More number of distillation columns may be required to separate and purify the desired product. Hence, reaction parameters are optimized to achieve greater selectivity. Higher conversion selectivity means greater yield of the desired product, hence lower production cost. Profitability of the operation depends on the production cost. It influences the investment decision making process. How do you arrive at the production cost? Raw material cost plus utilities cost equals a variable cost. Variable cost plus fixed cost equals a production cost. Let me now walk you through an example to strengthen your understanding as to how to analyze a PFR performance. The problem description. Allyl chloride is a petrochemical intermediate used in the manufacture of epichlorohydrin, which is used in the production of epoxy resins. Allyl chloride is produced in a plug flow reactor by thermal chlorination of propylene at 0.5 bar absolute pressure and 500 degrees centigrade. The key reactions occurring in the reactor at the specified operating conditions are described here. The main reaction is a substitution reaction between propylene and chlorine to form allyl chloride and hydrogen chloride. In parallel to the main reaction, side reaction is also taking place, which is an addition reaction between propylene and chlorine to form dichloropropane. There are some other series reactions are also occurring, which results in consumption of the main product. These are undesired reactions but are unavoidable. Chlorine is a limiting component and propylene is used in excess. Reaction 1 is a main reaction and reaction conditions are optimized to get the maximum possible allyl chloride yield. This figure illustrates the plug flow reactor for the reactions described just above with feed and product composition. Given here are the feed rates to the reactor and product from the reactor. Chlorine feed rate to a reactor is 1311 kg per hour. Propylene feed to the reactor is 3890 kg per hour. Allyl chloride produced is 1178 kg per hour. Propylene in reactor outlet is 3143 kg per hour. These flows are taken from a real world example. You are required to determine conversion, selectivity and yield for this reactor. In this example, you can observe that the reactor outlet does not contain any chlorine. That means chlorine has completely reacted. So chlorine is the limiting component and propylene is the excess component. You can use the mass flow rates to determine the conversion and other parameters. You can also use the concentration terms to determine the conversion. To determine the conversion, first determine the propylene reacted, which is 747 kg per hour. So the conversion is propylene reacted divided by propylene fed to the reactor, which works out to 19.2%. As expected, the conversion based on chlorine reacted is 100% because chlorine concentration in the outlet is 0. Selectivity. Selectivity is how much of the product is the desired main product. In our example, allyl chloride is a main product. Hence, reaction conditions are optimized to maximize propylene conversion to allyl chloride. The concentration of byproducts 4.6% by weight. Flow through the reactor 5201 kg per hour. Byproducts produced 239.2 kg per hour. So total products produced 1417.2 kg per hour. So selectivity for ALC is the mass of ALC produced divided by total mass of products. Substituting the values, you get the selectivity of 83.1%. Selectivity 83.1%. What is the meaning of this? It means only 83.1% of the products is a main product allyl chloride. The balanced reacted propylene and chlorine is used by the undesirable side reactions. Higher the selectivity, greater the quantity of product produced and more profitable the operation. In several petrochemical reactions, series reactions occur. The main product produced undergoes further reaction with the reactant to form undesirable byproducts, thereby reducing the selectivity. Yield. Yield is the ratio of mass of ALC produced to the maximum amount of ALC would be produced if there were no side reactions. In this example, chlorine is a limiting component. If there were no side reactions, all the chlorine would be consumed to produce a main product, allyl chloride. So the maximum possible amount of allyl chloride possible to produce is 1412 kg per hour. So the yield is 83.4%. This graph is an illustration of the change of concentration of reactants and products along the length of the reactor. Chlorine, being the limiting component, decreases progressively and becomes zero at the end of the reactor. Allyl chloride, the product concentration progressively increases along the length of the reactor. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Hope this presentation with narration and animation was useful. Please give your comments, if any, about this course after you finished viewing the video. Share with your friends and colleagues to reach out to a large number of career-oriented professionals and students who are desirous of developing job-oriented skills and enhancing the knowledge base. Thank you for watching.